Okay, welcome class, and we're going to go to notes here on my iPad to do 6.2 lecture on square roots and Pythagorean triples. Okay, so we have 6.2 square roots and Pythagorean triples. All right, everybody has their handout ready, and if you don't get that out, press pause on the video, get that out and ready. We're going to go through each of the examples and just kind of build our knowledge about square roots to deepen it. I know that some of you have seen this already before, and so we'll see in how it relates to Pythagorean triples. The first question asks us, the Geoboard lab asked you to build a square with area 2. Well, we didn't do the Geoboard lab, but we did use this idea about building a square with area 2 in our exploration from 6.1 of the Pythagorean theorem. Okay? So in part number 1, we had to build a square with area 2. So I'm drawing out some of these dots. Okay, I'm going to draw out this many dots. And it says in number 1, after that question, why was that more difficult than building a square with area 4? Okay, so here I have some dots set up for building a square of area 4. And so the square of area 4 is this big, 4 square units in here. Okay, 1, 2, 3, 4 square units. Okay, that's the square of area 4. But remember, the square of area 2 was a little bit trickier to do, because if you put the squares in a nice orientation here, we have either like 1 square unit or 4 square units. Okay, so area 2 was a square at a diagonal. Okay, and so that's why it was more difficult to build it, because you had to think diagonally. You had to orient your square in a way that you're not quite used to, in this manner. Okay, just like this. And remember that each one of these parts here of the square was a half, a half, a half, a half, so it makes 2. So the area here is equal to 4, the area here is equal to 1, the area here is equal to 2. Okay, if the square is area 2, which is continuing with question 1, how long is one of the sides? Okay, so here I'm highlighting one of the sides, bolding it, and we need to find out how big that is. Okay, so I'm going to draw a larger model square here of this, and so essentially what we're doing is we're finding the diagonal of a unit square. Okay, and so using the Pythagorean theorem, we're going to just complete this right triangle. We want to find out this length here. Let's call this length of the hypotenuse of this right triangle C. We're going to call this one A and this one B. So according to Pythagorean theorem, a squared plus b squared is equal to c squared. Okay, and this is kind of what we're going to do in the homework, so that's why I'm going to show you this now in a little bit more detail. We know that a and b is equal to 1 unit long. Okay, and then we have 1 squared plus 1 squared equals c squared, and we see we don't know what it is, so we have to leave that as a variable. So we have 1 plus 1 is equal to c squared, 2 is equal to c squared, and when you take the square root of both sides, which is the operation that undoes a square, we get c is going to be equal to 2 units, square root of 2 units. Okay, so that's the answer to the blank on this first one. If the area of the square is 2, how long is its side? Well, it's square root 2 units. What does that mean? Well, it means that the side length is equal to a number multiplied by itself, however long that is, to equal 2. And this drove the Greeks nuts because they wanted that to be a nice number. This one right here. They wanted this length to be a nice number, and it was hard. They couldn't find a whole number. It wasn't 1, it wasn't 2, square root 2, which is in between that. Okay. Going on to number 2. We have that many square roots are irrational numbers. Give an example of a square root which is a whole number. So square root of 2, for example, is not a nice number. It's between 1 and 2. But there are many square roots that we have as whole numbers. Okay. For example, we have the square root of 4. That's equal to 2. Okay, we have the square root of 9, which is equal to 3, and so on. So most of them are irrational, but some of them are rational. Okay. Okay, and that's the first blank here. And the second blank says give an example of a square root, which is an irrational number. Oops, sorry about that. We have the square root of 2, which is about approximately equal to 1.414. Okay, so there's, and that goes on forever. There's an irrational one. Okay, so these are rational. And this is irrational. Okay, so we have the first two things there. So we're going to pause this one as you guys think about it and load up another video. Okay, here's number 3. So number 3 talks about a general definition. A number is irrational. Irrational numbers. If what? Well, in this point in the lesson, I do a diagram which explains all of the set of numbers so we can build up to irrational. Okay, so here's what we'll do. The first set of numbers that are most basic are called the counting numbers or natural numbers. Counting or natural numbers. They are 1, 2, 3, and so on, going on forever. There's no fractions, no decimals, not even 0 is part of the counting or natural numbers. And that's one set of numbers here, and I'm going to put a thing around it, a circle around it. Okay. The next set of numbers that was including 0, and this is kind of developed historically, and those are called the whole numbers. And the whole numbers are 0, 1, 2, 3, and so on. Okay, and the whole numbers do not include any fractions or negative numbers either. Okay, but they do include all the counting numbers, and so I'm going to put a big circle around those. Okay. The next set of numbers are the where we start getting into negatives. Okay, even though fractions were developed more earlier historically, negative numbers are the next most basic number. And we, with positives and negatives, with 0, we call those the integers. Okay, integers. So there's things that go on forever from the negative end to -3, -2, -1, 0, 1, 2, 3, and so on. Okay, those are the integers. Put a big circle around everything because the integers do include the whole numbers and the counting numbers. The next one is going to be fractions now. Fractions. So we call those the rational numbers. Okay, rational numbers are numbers that are of the form a over b, where a and b are integers. Okay, so rational numbers are anything that can be written as a over b. Now I'm going to include every number because we can have some examples here. All fractions, some decimals. Okay. So other ones are like 1/2 and 0.5 because 0.5 can be written as 1/2. Other examples are 1/3 and 0.3 repeating. Okay, because even though it's a decimal that goes on forever, if it repeats, then it can be written as a ratio of two numbers. And that's where rational numbers comes from. It comes from numbers that can be written as a ratio. Okay. Now we're going to get into irrational numbers. And the irrational numbers are not rational. Okay. Irrational numbers are not rational. And so what they have is they cannot be written as one number over another. Okay, so those are including, so those numbers are going to be decimals, they're decimals that do not end, so they have to go on forever, and do not repeat. Okay, do not end and do not repeat. So those are the key points right there. All right, and so this is what the definition is right here. You write that in the blank for number 3. For number 4, which square roots are rational. Okay, so for number 4, rational square roots are examples of, like, if you take the square root of 1, 4, 9, 16, 25, etc. Okay, so the square roots make square root of 1 equals 1, square root of 4 equals 2. Let me back that up a bit here. 4 equals 2, and so on. The square root of 9 equals 3. And we touched on this a little bit before. Okay, square root of 16 is equal to 4. All right, and so on. All right. Now in number 5, we're going to skip because we're not going to focus on teaching too much. And in number 6, we're going to talk about the principal square root, which means just that we're talking the positive version. Okay, so let me move this up to here. And so for number 6, so 5 skip. Number 6, we're going to talk about principal square root. Okay, so the principal square root is the positive version of the square root. Okay, positive version. For example, we have the square root of 4 is equal to 2, right? Normally we say that because that's the most common. It's called the principal square root. But it's square root of 4 is 2 because 2 times 2 is equal to 4. The same thing multiplied by itself equal the number. Now, there's also another example where we can say that negative 2 times negative 2 is also equal to 4. Okay, and so because of that, we can say that the square root of 4 actually has 2 answers. Okay, it's actually plus or minus 2. But the principal square root is the one that we're going to be concerned with, and that's what we're going to talk about in this class. We're not going to worry about the negative ones. Our principal square root's just 2 times 2 is 4. So we're going to say the square root of 4 is 2, even though it actually has 2 answers. Okay, so there's one here and one here. Okay, so that's the end of this segment. And go into the next video. Take a moment to read over this and internalize it. Okay, now we're going to move on to number 7. Okay, so number 7. Here we're starting a section of our lesson where we're going to look at simplifying square roots. Okay, there's 2 rules that help us simplify square roots, and that's a product rule and a quotient rule. Okay, so the product rule comes first. The product rule is, according to your note handout, the square root of 2 numbers, square root of A, times the square root of B is equal to the square root of both of the numbers multiplied together, the square root of A times B. Okay, so that's the product rule. And we're going to use that, for example, we can prove the product rule by using the square root of 4 times the square root of 9 should be equal to the square root of 36. Okay, so you're multiplying the 4 and the 9 together. So let me back that up just a second. The square root of 4 times 9, which is equal to the square root of 36. Now we know that the square root of 4 is 2, and the square root of 9 is 3. The square root of 4 times 9, well, it's the square root of 36, and we know that the square root of 36 is 6, and so that checks out. So that's the product rule. The other part is the quotient rule. Okay, the quotient rule is just like the product rule, but with division. Okay, so we're going to have the square root of a number on the numerator, the square root of a number in the denominator, another one, and we're going to say that that's equal to the square root of them as a rational number, a fraction, a over b. Okay, so this is the rule, and so I'm going to give you an example again with the square root of, let's see, where we can have like one divide the other and be a nice number. Let's do 36 over 9, okay? So we're going to do the square root of 36 over here as the numerator, and the square root of 9 as the denominator. That should be the same as the square root of 36 divided by 9, okay? We know that the square root of 36 is, oh, sorry about that. The square root of 36 is 6. We know the square root of 9 is 3. And we know that the square root of 36 over 9 is 4. So we use the square root of 4. 6 divided by 3 is 2. And does that equal 2? Yes, it does. Okay. So the quotient rule does work, and the product rule does work. So those are two rules that we're going to use for arithmetic with square roots. In number 8, we have a bunch of problems, A through H. How about practicing simplifying with square roots? And so this is kind of like the main part of the lesson. In part A, we have two things added together. 3 times the square root of 2 plus 5 times the square root of 2. Okay, now we're trying to simplify that. Okay, make it simpler. Now, that's 3 multiplied by square root of 2, 5 multiplied by square root of 2. Using the definition of multiplication, this right here is 3 groups of square root 2 added together. Right? And then this one right here is 5 groups of square root 2 added together. Okay? And so if I'm going to go ahead and write all those out, so square root 2 plus square root 2 plus square root 2. So that's what we have is 3 groups of square root 2 there. And this is 5 groups of square root 2. Square root 2 plus square root 2 plus square root 2 plus square root 2 plus square root 2. Okay, so I'm adding them together, and so I should actually put a, this one right here. Should actually put a big add here, because it's from this one right here. Right here. So this one right here goes down here. Okay, so I'm adding them all together, and so when you add them all together, we have the same kind of thing added together. So that means it's also repeated addition, which is another form of multiplication. How many groups of square root 2 do we have? So we have 1, 2, 3, 4, 5, 6, 7, 8. Okay, so when I add those together, I should end up with 8 square root 2. This is the long way. I have 3 groups of square root 2 added to 5 groups of square root 2. And since I have 3 of them and added to 5 of them, I should get 8 of them, right? Okay, so the answer to the first one is 8 square root 2, part A. Now part B is going to be, I'm trying to add the square root of 3 and the square root of 5. Okay, now those ones aren't like each other. Okay, the square root of 3 is a very long decimal, and so we're trying to see what to do with this here. So we have 3, we can calculate that. The square root of 3 is actually approximately equal to 1.73205008, and so on. Okay, it goes on forever. And I'm going to try and add that to the square root of 5. Okay, so we're going to do the square root of 5. Oops. And we get 2.2360679, and so on. Okay. Now, since these two numbers go on forever as decimals, I don't know where the end is to actually add them together. And when I do add them together, they don't make anything that's like a square root. And so that's why, in order to keep things short, we leave it in this form if the square roots are not the same number. Notice that in part A, we have the square root of 2 and the square root of 2. Those ones are like each other, so I have 3 of those and 5 of those, and they make 8 of those. Okay. But in this one, I only have 1 square root of 3 and 1 square root of 5. And those numbers are different enough that you can't add them together to make one nice number. And so what mathematicians prefer to do is just keep it like this. Okay, keep it in this separated form with the square roots. Okay, they call it the exact answer. And these are called decimal approximations. Okay, so that's how we're going to handle in our class any square roots that are not like each other. We're just going to keep them separate. Okay, so going on to number C, we have 4 square root of 5. Subtract the square root of 5. Okay, remember that this is not going to be just 4. Okay, it's a common misconception. Okay, since this is 4 multiplied by the square root of 5, not added the square root of 5. Okay, so if it was added, then it would be 4, but it's not. It's multiplied right here. Okay, so it's multiplying. And so I'm going to go ahead and back this up a little bit. What is it? Okay, in all actuality. Okay, so we have 4 groups of the square root of 5. I'm going to take away one of those square roots of 5. Okay, so remember, we have 4 groups of square root of 5, so it's the same as square root of 5 plus square root of 5 plus square root of 5 plus square root of 5. Okay, 4 groups of square root of 5. Then I'm going to subtract off a square root of 5. Okay, so here's my 4 groups, and if I subtract one of those off, that will simplify here. Okay, and what I end up with, and I'll move this back up here, is I end up with just 3 groups of square root of 5. Okay, so 3 times square root of 5. So if I have 4 square root of 5s and I take away one of those square root of 5s, then I only have 3 square root of 5s left. Okay, so the answer to that one is 3 square root of 5. So moving on, we have part D. And part D has 2 square root of 3 plus 5. Okay, so I have 2 square roots of 3 and added 5 together, which doesn't really add together because I have square root of 3 plus square root of 3. Plus 5, and so they just don't, we just have all different like terms. And so it's easier to see, except for these two, it's easier to keep those together. So what we're going to do is we're just going to say that this is the answer right here. So we don't just have just random square root 3's going around. Okay, so that's the answer to that one. Can't combine them. Okay, is what I say in my solution set. In part E, we're going to go ahead and start doing multiplication of square roots. Okay, remember square root 2 times square root 3, according to our product rule, is going to be the square root of 2 times 3, which is equal to the square root of 6. Okay, so that's that one. Moving on this on up, we're going to go ahead and continue on with part F. Okay, in part F, we have 2 square root 2 multiplied by 5 square root 3. Okay. Now here, we need to see what's going on using our product rule. Now, these are multiplications in between here. Okay, I have whole numbers, 2 times 5, and I can switch those around, right, because of the commutative property. And the ones that are left are square root 2 times square root 3. Okay, and so when we simplify this, we get 10, and 2, and according to the product rule and part E, I know that that's going to be equal to the square root of 6. Okay, and so that's our answer there. So 10 square root 6. G. Now G is 6 square root 3 times 4. Okay, you have to be careful on this one because there is not an addition in here. Okay, that is not adding, and you can't distribute. Okay, you cannot distribute. So when you do 6 times the square root of 3 times 4, I can just use the commutative property and multiply it, switch it to be 6 times 4 times square root 3. Okay, and when we do that, we just get 24 square root 3. Okay, so that one's pretty good there. And H, we have 2 square root 4 times 5 square root 3. Okay, and with this one, again, we'll use the commutative property like in F. We have 2 times 5. And I'm just noticing a couple of ways to do this one. So we'll do 2 times 5 times square root 4 times square root 3. Now, when we simplify square roots, we look to simplify as much as we can before we multiply, just like in fraction multiplication. And so if you notice, the square root of 4 is actually 2. Okay, and so what I can do is I can just make that a 2 from here to here. And we have 2 times 5 is 10. 10 times 2 is 20. So 20 square root 3. Okay, that'll be the easiest way to solve that problem. Number 9. Number 9 has a bunch of examples too. And we're doing simplifying square roots. So when we simplify, we're going to actually break up our numbers into factors. Okay, so part A is we're thinking about how to simplify the square root of 20. Okay, the square root of 20 can be thought of as the square root of 4 times 5. Now I'm breaking 20 up into these factors because the 4 is actually a nice square root. And I'm taking the product rule and I'm using it backwards. Okay, so remember that the square root of a times the square root of b is equal to the square root of a times b. Okay, so recall this. Okay, and I can also go backwards. Oops, sorry about that. And say that the square root of ab, a factor, a number factored, is the same thing as the square root of a times the square root of b. Okay, so we have that little recall there. And so when we do the 4 times 5, we're going to do the square root of 4 times the square root of 5, okay, by the product rule. Square root of 4 is 2, and square root of 5 stays the same. And so our answer is 2 square root 5 on that one. Okay. Part B. Part B has 5 square root of 28. Okay. Again, we're going to find factors of 5, square root of 28. Okay, so I want you guys to pause the video and try and work on this one on your own. Okay, and think of the factors of 28 that have a perfect square in them, where the square root is rational. Okay, is a nice number. So go ahead and pause the video. Okay, now that you've probably resumed, let's see how you guys are doing. 5 times the square root of 28. So we have 5 times the square root of 4 times 7. Okay, so 4 is that perfect square. So that's the same as 5 times the square root of 4. Oops. Right here, 4 times the square root of 7 using the product rule. Okay, and that's going to be equal to 5 times 2 times square root of 7, which is equal to 10 square root of 7. Okay, and so that's the answer to that one. C, we have 2 square root 12 times 3 square root 75. And what we can do with this one is we'll also think about ways to break apart or factor 12 and 75 into perfect squares. Okay, so go ahead and take a minute to work on that one. Pause the video, and when you're finished, you can resume. Okay, so now that you've worked on that, we're going to break up 12 into 6 and 2. 2 times, sorry, that wouldn't work. 4 and 3. Yeah, 4 times 3. And we're going to multiply that by the 3 times the square root of 75. 75 we can break up into 25 times 3. Okay, so now what we have is 2 times the square root of 4 times the square root of 3 times 3 times the square root of 25 times 3. Okay, square root 3 there. Then we have 2 times square root 3 times 3 times 5 times square root 3. All right, and we're going to multiply our numbers together. 2 times 3 times 5 times square root 3 times square root 3. 2 times 2 is 4. 4 times 3 is 12. 12 times 5 is 60. 60 times square root 3 times square root 3. Okay, remember using the product rule, we can put those two together. 60 times the square root of 9. Oops, let me not jump too quickly. 3 times 3, which is equal to 60 times the square root of 9. Okay, we know that the square root of 9 is 3, and we know that 60 times 3 is 180. Okay, notice though, which we'll use later, is we have the square root of 3 times the square root of 3. That one, when you multiply it all together, gives you just 3. Okay, so that kind of thing we'll find out in the homework and throughout the lesson here. Okay, so that one is 9C. Moving on to 9D. Okay, so we have 9D, and we're going to do 5 over the square root of 2. Okay, so 5 over the square root of 2 is 5 divided by the square root of 2. Now, when we simplify, mathematicians these days say that you need to not have any square roots in the denominator of a fraction. Okay, And so here's the trick to what we call rationalize the denominator. I'm going to multiply by the square root of 2 over the square root of 2. Because remember up here, we had the square root of 3 times square root of 3 gives you 3. So that will give you a rational number. So multiply the number denominators by the same number so that you can have rationalize it here. And in order to not change the value, you need to multiply by the square root of 2 over the square root of 2, the same number over the same number. Okay, and so when this right here gives you just 2, as we've said before, kind of like using the steps above here, and then 5 times the square root of 2 is 5 square root of 2. Now sometimes this part can simplify, so watch out for that. But since it can't, we have 5 square root 2 over 2 is our answer. Okay, so part E. Just 2 more. You guys are hanging on great. Feel free to pause the video at any time. Okay, let's have you pause it now and solve square root 12 over square root 3. Simplify it. Okay, so moving on, we have the square root of 4 times 3 over square root of 3. That's equal to the square root of 4 times the square root of 3 over square root of 3. Notice that these are the same and they can cancel. Square root of 4 is the same as 2, so that's our answer there. And then the last one is F, 6 square root of 18 divided by 5 square root 12. Okay, thinking of perfect squares that can divide into 18, 6 times the square root of 9 times 2 divided by 5 times the square root of 4 times 3. Okay, so we have 6 times the square root of 9, which will be 3, and square root 2 divided by 5 times square root 4 times square root 3. Okay, and then we simplifying them, we have 6 times 3 square root 2 divided by 5 times 2 square root 3. And when we get our final answer, we have 18 square root 2 over 10 square root 3. Now there's a square root of 3 in the denominator, and so we got to take care of that, which means that we multiply both sides, the top and bottom, by square root 3 over square root 3. This will make 3, right? These two together make 3. And so we have 18 square root of 2 times square root 3 over 10 times 3. And when we simplify this more, we get 18 over 30. Oops, here I'm going to run out of room. Back up a bit. We get 18 square root 6 divided by 30. Okay, and 18 over 30 can simplify by 2's at least, so 9 over 15. Square root 6 comes along for the ride. By 3's now, 3 over 5. So 3 square root 6 over 5. Okay, so let's go ahead and take a break there. Okay, welcome back. We are going to continue with number 10. Okay, number 10 starts a section of our lesson on Pythagorean triples. Okay, so on the graph paper that's attached to this handout, we need to draw 3 right triangles. The first one has legs of 3 units and 4 units, and so I'm going to just draw it over here. So 3 units. Okay, so let me back up a little bit. Okay, so 3 units long. 1, 2. I'm going to use those as kind of like the dot paper. You can use them as grid squares. There's 3 units that way. And then the other leg is 4 units. 1, 2, 3, and 4. Okay. So what you're supposed to do after you draw those is that you're going to measure the hypotenuse. So I'm going to construct the hypotenuse and measure it. Okay. So you go ahead and do this on your graph paper. Pause the video, draw out the legs, and then draw the hypotenuse and then measure it. Okay, so now that we're back, this is 3 units, and that's 4 units. It turns out that this distance from here to here is exactly 5 units, if you notice the measuring on that. Okay, 5 units with your measurement. Okay, and so we're going to do notice that are all whole numbers, which is like amazing, right? And so Pythagoras also helped discover this, and that's the first part. This is triangle 1. Okay. Triangle 1. Now triangle 2 is the same way, so let's go ahead and do that one. on your paper. So you can follow along on your papers. Triangle 2 has one leg is 5 units and the other is 12 units. So 1, 2, 3, 4. Actually, I'm going to draw small units here. So 1, 2, 3, 4, 5 units this way. 1, 2, 3, 4, 5. Good. And then it's going to be 12 units going the other way. So the other leg is 12 units. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so the 12 units this way. 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, and then we draw the hypotenuse of the triangle number 2, and you measure it. Okay, so what we have here is 8 units, and this is 12 units. And the measurement for this one is going to end up being 13 units exactly. Okay, so go ahead and verify that on your paper by pausing the video. Okay, next, the last one is going to be a triangle with 8 units for one leg and 15 units for another. Okay. Okay, now I made a mistake on that one. This one's supposed to be 5 units. Oops, eraser. 5 units. Okay. All right, so next, this one is 8 units and then 15. Okay. Okay, so we have 8 units this way. I'm going to write this down just to help me remember again. 1, 2, 3, 4, 5, 6, 7, 8. So 8 units this way. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, so that's about 15 units that way. And when you measure this one, 15 units, so remember there, I'm going to measure this distance here, the hypotenuse of the right triangle. Okay, that's right, right, right. And this one is actually going to be a nice number 2, which we have 17 units. Okay, so go and verify that on your paper. Moving forward, we have number 11. Number 11 says that usually the hypotenuse of a right triangle has an irrational number, but it would be wise to memorize 7 cases where the hypotenuse is a whole number. Okay, wise meaning that you can do some problems faster. Now, if memorization is not your thing, you can always verify this and find the answer using the Pythagorean theorem. Okay, so what they say in some sample Pythagorean triples are the 3, 4, 5. Okay, so part A is a 3, 4, 5 triangle. That's the most famous one. Part B is 6, 8, 10. Now, it's 6, 8, 10 works because notice that each one of these numbers have been doubled. Okay, you can double the size of the Pythagorean triple of the right triangle, and you'll have another right triangle with nice rational numbers. Okay, you can double it, you can triple it. Okay, you can triple it, and this is like part from number 5 here. Triplet is making 3 to 9, 4 to 12, and 5 to 15. Okay, so tripled from here. So we're going to go back that way, and so from here to here is tripled. Okay, that also makes a nice right triangle. Okay, so the other ones are similar to what we've just done in number 10, where we have, let's see it, a 9, 12, 15. Other ones, yeah, are 9, 12, 15, 5, 12, 13. Okay. We have an 8, 15, 17. And other variations of those where they're doubled or tripled. Okay. So those are Pythagorean triples. Now number 12, which is our last problem, is using Pythagorean triples to determine the missing length here. So I'm going to redraw the triangle. And we have 130 feet. We have 120, whoops, that's x feet. We're trying to find that one. And then this one is 50 feet. Okay, so take a moment, pause the video, and find out what x is. Okay, resuming on, we can find x using the Pythagorean theorem, because this will be, let's set this one to be a, and this one to be x, or b, and then this one to be c. Okay, so we can find it first way. So first way is going to say, okay, here's how I'm going to find it with the Pythagorean theorem. I know that the Pythagorean theorem, oops, sorry about that, is a squared plus b squared equals c squared. Okay, so I'm going to do 50 feet squared plus x feet squared equals 130 feet squared. Okay, so a squared plus b squared equals c squared. Now 50 feet squared is going to be, sorry about all that, is going to be 2,500 feet squared plus x feet squared is equal to, now 13 times 13 is 169, and then 0 in the zeros, we add 2 of them on because we're squaring. Okay, all right, so to find out x feet squared, we're going to subtract 2,500 from both sides because we want to get just x by itself. Now that will simplify there. Take off that many feet squareds, take off that many feet squareds. Okay, and 169 minus 25, so I'm going to do that one on my calculator here. And I get 144, so 14,400 feet squared. That's what x squared is. So therefore, x is going to be equal to the square root of 144,000, or 14,400, and which is going to be 120. Okay, so this is feet squared. I'm taking the square root of the feet as well here and to make feet at the end. Okay, so x is 120 feet. All right, well, that's our lesson. I'm going to go ahead and post a video about doing the first homework, for example, so you can get an idea of how those go. Okay, welcome to the homework example that I'm going to do for you. So in homework set 21 and 22 on the Pythagorean theorem, 21, 22, Pythagorean theorem. We have, the first problem says, two boys are cutting across a diagonally a 50-foot by 100-foot vacant lot on the way to school. So how much distance do they save by not staying on the sidewalk? Okay, we need to round our answer to the nearest foot. Okay, so there's number one. So this is a place where we can just draw a diagram here. Oops. Of a rectangular lot. My rectangle needs some help. Okay, there we go. There we go. In this homework, all of the situations have a right triangle associated with them. Okay, so here is the lot, parking lot. It is 150 foot by 100 foot. Okay, so we have 50 feet, this one, and 100 feet, the longer one. Okay, how much distance do they save by going across the parking lot? So they want to go and trek across here. They want to go this way. They're coming around this way. And then they're going this way. And they're going to walk up this way. Okay, so because they want to go from this point to this point. Okay, so that's the way that they would go on the sidewalk. Okay, these boys are not very patient, and so they want to go across like this. Like that. And so what we have here is a blue right triangle. Okay, so we have, we're going to assign the 50 and the 100 to A and B. So I usually use A as the smaller length and B as the longer one. And then we have C here. We don't know what that is, so we're going to use that as C until we find out the answer. Okay, so we find out, the plan is to find out this distance here. And we want to take that distance, we find that, and we find out how much they're saving. So remember that we're going to take that distance and we're going to subtract it from 150. Okay, so first let's find this distance. Okay, so using the Pythagorean theorem, which in this homework, you're just always going to use this formula. A squared plus B squared equals C squared. Remember, the Pythagorean theorem says that the area of the square off of one leg plus the area of the square off of the other leg is equal to the area of the square of the hypotenuse. Okay, so we're going to substitute in A and B. And in this homework, some of the numbers are going to get big because they are real life. Okay, so we have 50 feet here. We're going to square that. 50 feet, sorry, not 50, but 100 feet here. And we're going to square that. And that's going to equal to C squared. We don't know what that is again. Okay, so when we square the 50, we're going to square the 50 and the feet. And so that's 2,500 feet squared. And if you don't know your squares, then go ahead and simply use a calculator to find out this. So use a calculator a lot through this homework. So hopefully you have one of those. And 100 times 100 is 10,000. Because I have 2 zeros here, I need 4 here. Okay. So it's 10,000 feet squared equals c squared. Okay, so when I'm going to add those together, I get 125,000, I believe, 12500 feet squared equals c squared. And when you have, sorry, it's 12,500. And when you have those numbers there, it's probably not going to be very nice. So that's why you also need to use your calculator and the square root button. So what we're going to do is you're definitely going to take the square root of both sides. And when you do that, c is going to be left over on that side here. And I'm going to switch it because I like to put the letters first. And then when you take the square root of 12,500, you get about 111.8 and so on feet. Okay, and so because you've done that, we found out what this answer is here. So I'm going to erase this question mark, put in the answer of 111.8 feet. Okay, now remember that we are not quite done, and that we want to find the distance is saved. Okay, so I'm going to put this up here. And the distance that is saved is the distance that you have total around this way on the parking lot, subtracting off of this way to the parking, from one end of the parking lot to the other. Okay, so we have our 100 feet that we're going to go to first, add that to our 50 feet, and then we're going to see what that distance is there, and I'm going to subtract off the part that is, we subtract off that part that we actually calculated. Okay, so we can see how much is saved. So it's going to be 150 feet, subtract off 111.8 feet. And using my calculator, I get about 38 feet. Okay, that's the distance they save. Okay, so this is one example of the type of problems that you'll have in the homework. Find the right triangle, set up the right triangle. You will be given 2 of the 3 missing variables, and just simplify. Substitute in to the Pythagorean theorem, which is here. Substitute in right here, and then simplify. So we use the Pythagorean theorem. Substitute. And then this part down here is simplify. Again, you'll need to simplify by using your calculator to these decimals. And what they do is they pay attention to what they're giving you as the way where to round. Okay, so hopefully you enjoy the homework. I found that these problems were interesting, much more interesting than the ones in the book. So that's why I assigned those. Good luck, and let me know if you have any questions about anything. Send me an email. Thank you guys. Have a wonderful day.